Okay, here comes a little bit of reminders of what we have gone over and what is most likely going to be on the final exam. I just made some notes, threw them together here. There's a couple of difficult, I call them complicated questions. That one, for instance, 45 is a question that's going to be on there. And what it's about is I call it walking backward to obtain the mass retained, the percent mass retained when you're given only the percent passing. Now, I did this a year ago, or whatever the last time I did this. I did it one way, then I did it another way this time, but we will get there in just a minute. Uh, and let's look over the final. I don't know, those are my notes. Don't forget about the rock weathering and the soil formation, the types of deposits, alluvial. What are they? Residual, that's where they happen in place. Alluvial is carried by water, those kinds of things. Just skim through your book. Uh, uh, how are they classified? Like, how are soils classified? Okay. So one of them is like, one interpretation of that could be cohesion, cohesionless, and organic, you know. What about the states of the plastic? There, there was this little guy here, and it was shown to illustrate, limits. What is this? Liquid, uh, semi, solid. Uh, am I right here? Plastic, and then the key to this thing, it was showing you how the volume increases as you're moving through these limits. This one limit between semi-solid and liquid limit is notable for some reason, and it's slipping my mind. Is that the something to do with how dry you can get one of them rolled up plastic worms before it starts cracking? There's some language in there about that, and I think this is the line for that. You might go look for that. Remember the hydrometer test, and that measures the composition. You can get the clays and clay-like matter from hydrometer test. Also, activity. Remember the, what is that one called? Plasticity index? No, the liquidity index. That's where you find the activity of the soil and go back to the history of the soil to see if it's if it's still under stress and things of that nature. I don't know the questions, but this plasticity chart is a simple, I don't want to say gimmick, that Casa Grande, I'm not sure they use that anymore. It's in that FE handbook to study to be an engineer, but just to refresh your memory a little bit, I put up a little scenario here. If uh, if you had a soil that had a liquid limit of 60 and a plasticity index of 35, how would you classify that soil? Well, the way to do that is go to this chart. On the x-axis, we have plasticity indices from 4, 7, 10, 20, 30, 40, 50. On the x-axis, this is the y, this is the x, or this is the ordinate, I mean abscissa, this is the ordinate, whatever your background is. But so we have a liquid limit of 60. I shouldn't have put that. That's going to throw us. Let's change that to, that's going to put us above the U line. I don't want to do that. 40. So we take a line on this 40. No, it was supposed to be 35. That's what, there it is. Plasticity index of 35, liquid limit of 60. Now, I got myself together. I wanted it to be within this area here. You get above the U line, they call it, and soils are questionable if they fall up in here. But the way we classify soil using this chart, and it's at the end of the Unified Soil Classification System, the final touch you put on a silty clay or sandy clay, like we had in that example of classifying a soil I went through rather quickly. So our point is right here, and we're in the area that is either clay with low plasticity, low plastic, or organic with low plastic. Or up here, we're more in the clay with high plasticity, or organic with high plasticity. And so this soil right here could be a clay with high plasticity. This up here, where we are, could be a clay with high plasticity. So this is the plasticity chart. It's one of those things you probably need to know. I've written on front and back, tried to number these. Talk a bit about the classification of soils, and that's actually what all this is about. But when you're using the AASHTO classification chart, you want to look first of all for things you can rule out. And by that, I mean that won't apply. When you look at an AASHTO chart, you're going to see, I start with this guy, number 200 sieve. It's 33%. So what kind of soil do I have? Do I have a granular soil, or do I have a silt clay material? So the way you know is if 35% or less is passing through the number 200 sieve, you have a granular soil right there. You go up here, 33% is passing, so that's less than 35%. So you're going to be concerned with these guys up here primarily, because your sample is mostly coarse grain. Now, shuffling my papers, I'm getting them mixed up. Oh, they're under here. So we were talking about soil classification, and I throw this in here and talk about this AASHTO thing. And right quick, remember, as you recall, that fella on a couple of maybe videos did this. But when you look at this, you put your, here is 77. That's percent passing for number 10 sieve. 51 is the percent passing for the number 40 sieve, and 33% passing, which categorized our soil as granular, is for the number 200 sieve by definition. So there's the first thing we can do, like I said, is we have a granular material. We don't have a silk clay material. There are times if we were over 35%, if 40% or less was passing, we would have a silk clay material. We'd only be concerned with this area over here. So, but in this case, so far, we're concerned with pretty much everything. So let's take a look here just for a little bit. I don't want to spend a whole lot of time on everything. So right here, we'll start with the number 10 sieve. Is it less than or greater, or is it over 50 is what this is saying? 50 max. Yes, it is. So we can't go there. We have to go down. 51, 30 max, can't go there. Moving. 50 max on 40. 51, nope, can't go there, but we can go here. So we got to start. I kind of circled that, it looks like. We got to start here. Now 33 passing. This is 15 max, can't go there. 25 max, can't go there, can't go there. 35 max, that's a possibility. What we want to do is classify, is get past everything, and that tells us our soil. Here's a for instance, I'll get to it in a second, but see, we got past the A27, we got past the 11 minimum for the plasticity index, we got past the 41 minimum because it was 46, the liquid limit was, and we got past the 35 max because we were 33 on this passing the number 200. So we already know what kind of soil we have in this case. We have an A27 soil. Now, from there, we know that A27s and A26s, I believe it is, we only use what's called partial group index. Now, the partial group index is half of the regular group index. Now, I'm going to throw that in front of you right quick so you'll see the difference. Regular group index. So if you look where this plus sign, this is a calculation right here, a formula. Some people call it an equation, but it's not. But it's this amount right here, whatever that turns out to be, which will be down here after we're through. It's this amount plus this amount gives you your group index. Minus 46.4 plus 1.26 gave us 0.8 for our group, so we called it 1. But this is the partial group when you're dealing with A27s and A26s, I think. We have an A27, so we would do a partial group that I've done right here. And real quick, we have 33% passing you remember our calculation, this is the percent passing the number 200 sieve, minus 15. That gave us, and then it's times 17 minus 10. See, you can go back and see I'm not doing anything. I'm just using this side. They call it the kind of the plastic side over here. It's called the partial group. That's all we're required to do on an A27. So as I go down through here, first of all, I'd go PEMDAS. You know, I have parentheses here, so I can get rid of those. And 33 minus 15 is 18, or it was when I calculated this. So I think it still is. And 17 minus 10, that's in the formula, is, I think that's liquid, that's plastic index right there. 17 minus 10, that plastic index minus 10 is the formula. So this goes to 18. This right here turns into 7, And then I'm removing parentheses and brackets and things. And then when we multiply 18 times 7, we get 126. And then we go over here and we multiply that 126 by 0.01, and we get 1.26. That's our group index for that soil. We have an A27, and basically we have a 1. So that's a curly equal, kinda equals is what they call it. Okay, so that's a AASHTO classification situation. Now, let's see this is 2. We went through soil classification. We just went through a group index. By the way, if you are studying and run into something that you can't figure out, you can shoot me an email or give me a call. You should have my information. It's on the syllabus. But here's that formula for the partial group index. It's 0.01 times the number of particles passing the number 200 sieve. In this case, well, that case a while ago it was 33. So I don't know, 60.2 in this little, if we were working on that. So know how to classify the following: percent passing, and know when to use liquid limit. Remember, we used it over here. Don't forget how we used that, because I don't want to take up half a day going through this and probably end up getting you confused. But we use that liquid limit down here to get this A7 group done. We got to 35 max because we have 33 here, so that got rid of that. And on our liquid limit was 46, so we had a 41 minimum, so the 46 would work. So it wouldn't work at 40, but it worked at 41. And then here we have the index at 17, plasticity index at 17. That's my liquid limit minus plastic limit. Right here, 46 is plasticity index is 17. So you go across here and it has an 11 minimum, so we're good there. So that's how we came up with an A27. This is how we calculated the group index. Now, I think I'm going to put this out of the way. I'm going to put, if you have questions, ask me. If you want to come back to the plasticity chart, let me know. But for now, I'll put it out of the way. Here's our AASHTO classification that we just did. Let's put it out of the way. Here's another glance at the full group index. As you can see, it's just two things we have to look at. We have to look at this side of the plus sign, and you see this turned out to be a negative. Notice that. Don't forget little things like that. 30, because it started out percent passing fines was 33%. And this is a constant. It's in all of the calculations. So it's the percent passing the number 200 sieve, which happens to be 33%, minus 35. That's where the minus 2. So it stays with us, if you notice, all the way till we got down to here. And then on this calculation, I won't go through it, but you can see it's just going down, down, down. And again, we're just adding all of this stuff to all of this stuff to get the group index. Okay, if we have to, we'll come back to it. I may do these a little bit out of order, but I'm going to go through this. I just kind of went through it a little bit, but here it is all written out. This is coming up here in a minute. The mass retained, the percent of total mass retained, and then the cumulative. I hope you remember how to calculate that. There's a example coming up I have though. So using percent passing, start in column A1A. That's this is kind of a storyline for this. Start in column A1A, and that's where you start using these percent passings right here. And then you must be able to satisfy. Satisfy means that it will get past this 50 max. It's 77, so it can't. This is 51, it can't get past that 30 max. This is 33, and it can't get past that 15 max. Okay? But when we get on down, we keep moving to the right with this one right here, and we got 35 max, so we can, it'll work there, it'll work there, it'll work there, and it worked here. And that was using the percent passing, the number 200. Now when we get down to liquid limit, this 41 minimum, and we have 46, that'll pass it, that'll satisfy that. 40 max, no, it won't satisfy that, but again, it'll satisfy that 41 minimum, no, but yes. And this yes is what selected our group for us. And again, there's that partial group calculation down there. So that's all I'm talking about here. You will be working only with, if you have over 35% passing the number 200, you can rule out granular, and you will be working only with the A4s through the A7s, and that's over this group right in here. You won't be dealing with any of this. And this group honestly really uses the liquid limits and the plastic size, the characteristics of fractions passing the 0.425 or number 40 sieve. So that's what that little explanation was about. Speaking of percent passing, let's see if I didn't forget. So this is what we have when we're going to start with to come up with values that would help us create grain size sieve analysis, the curve thing, that thing. So right here, these are mass retained. These are the sieve numbers, right? So let's go, maybe we'll do a couple of them. Here is your total. This is what you got to know first. This is your total sample size. I have about worn pencils out. I'm working on this a couple of days. The total grams is 375. So if I want the percent of the total, in this column right here, I have the mass retained is 45. So the percent of the total would be 45 divided by the total sample, 375, and that's going to be, turn me on, 375 divided by 45 equals, and that's equals 8.3, but that's times 100, right? Is that right? 375, 40 divided by, no, I did that backwards. I'm sorry, guys. No, I didn't. I put it in backwards. 45 divided by 375. See if I can get it entered right. 45 divided by 375 equals 0.12. Multiply that times 100 to get a percentage, right? All percentages are based on 100. So I've got 0.12 times 100 equals 12. So that equals 12. So far, I've accumulated 12%. Cumulative means we're going to keep adding to these things. Okay. So the next one is I have retained 3.6. So 3.6 divided by 375. That equals a little bitty bit. It should equal a little bitty bit. It's only 3.6 grams. So that's times 100. So my answer is 0.96. My percent of total goes here. Sorry. 12. So 12 and then 0.96 for cumulative. 0.96. Remember, I got to add that. 0.96 plus 12 equals 12.96. That goes right here. I take this and I add it to that, and I get 12.96. That's cumulative percent total. Cumulative, because that first is 12. This is 12.96. Now then, let's look at this one. Has 71.3 divided by 375 times 100. Let me clear it. Now I'm not going to work all of this. I'm just going to get you started on it. Have I done it yet? No. 71.3 divided by 375 equals 0.19 times 100. 19. So we have 19 here plus 12. We got 19 plus 12.96, and that equals 31.96. So that's how you do it. You keep doing the same thing all the way down. We first get the percent of total right here, and then since there's nothing above this, it just moves over here to 12. But we get here, we get the 0.96, and we add that previous to it right here. We could add it here if we wanted to, but let's stay over here. Add 12 to 96, so 12.96. Same thing here. We multiplied, we got 19, but we got to add that, and gives us 31.96. So that's calculating percent passing. Now, to get that percent finer, we'd go all the way down here. To get this percent finer passing, percent passing, all of this other is retained, percent retained, percent of total retained, cumulative percent of total retained. So this is what's passing. And the way you get it is we're talking totally 100%. This is 12%. So take 100 minus 12, and that's going to be your percent passing. So let's do that. 100 minus 12 equals, so we got 88 passed here, and that's pretty typical of the number 4, a high number. So we got 88% passing from the number 4 sieve, which is what, 0.04 something, little bitty guy. And so we would do it down here. 100 minus this 12 point, that's the rest passed. This is right, retained. And 100% would be to find out what the difference between what was retained versus what passing is, to track the retention particles from 100. 100 minus 12.96 equals 87.04. No. Yeah, 87. We could express these as whole numbers down through here, by the way, and it'll eliminate some of these fractions. You can express it like express as whole. Some people require or prefer that. So there's the way you do the calculate percent passing. And these guys right here start helping us with other things that we got to do, such as eventually get here 60% passing, 50% passing. You line these dots up. Look up here. I don't know if you remember the 3/4 passing. And I don't know what I did with it. But see, the 3/4 is almost 100. And we came up with 88 on the number 4 sieve, but this is even smaller. So that's what this is leading up to, is we take the sieve number, like sieve number 40, this is percent passing. The sieve number 40, it doesn't list this opening, and I don't know, but I think I would have to guess at it. But I don't want to do that. I don't want to do that. See how quick he is at looking up things that most engineers, of which I'm not, most engineers would know. So the number 40, is that what I said? Number 40 is a 0.425 millimeter opening. So go back over here, 0.425 is, this is 0.1, 0.2, 0.3, 0.4. Be right in here would be that. And this would go to the percent passing. We didn't figure, but whatever that was, if it was 30%, we would go up here and put a plot. That's the way you do it, this versus this. These will be used for another thing here in a minute too. But that's how we plot that curve, based on the percent finer than the sieve right here. And this is the Simlog paper. It starts at 1,000ths, starts at 100th, 0.01, and then it gets to a tenth here, and then it's 1/10, 2/10, 3/10, like that. So don't want to spend some more. We got more things to do. So that's calculating percent passing. We talked about calculating AASHTO. We did calculate an AASHTO. Now, there's a problem in here that's going to tell you, OMG, how to start with percent passing. Where's that little thing I just had? Start with what you're given and not know any of this and be able to calculate this from percent passing. Now, I don't know if I made this up, the numbers to start with. I don't think this will be the problem, but it's going to ask you to do this. I'm going to put our grain diameter curve away. Now, there's a question that says, give me a minute, it's kind of worth reading. Yeah. If it's handy enough. If it's handy enough. That says, it's question number 45 that this is, this conglomeration's gonna be talking about. These are some of my explanations down here. Get to it in a minute. But it says, to find, it wants you to find the mass retained, which is, mass retained would be like, not the percent. It wants you to find the percent mass retained, and it wants you to find the mass retained, the percent mass retained, the cumulative percent mass retained, and these are not given to you. This to my right of my hand is all that you get. Now, how in the world? You know, these kind of problems. I don't know. Actually, the first time I did it, I don't even know how I did it, but just kind of breaking it down to how my mind went, and others I've talked to, is let's look at a for instance. Let's take this number 10, and if we go over here, we'll say right now we're given these right here. That's all we're given. 2%, 4%, 16%. But let's take this number 10 sieve and let's start with 46% passing. From this, how can I determine this? Where in the world did that come from? You know, what is that? That is cumulative percent right here. And to get percent passing, we've got to subtract cumulative percent from 100. But how did we get the cumulative percent? Well, let's go down here and look. Still talking number 10 sieve here. If 100 minus x, and that is 100 minus something, is equal to 46. So 100 minus, we don't know this yet. Whatever, this is x, let's call it x. But 100 minus that value is 46. So how do you find that value? Well, let's see. If 100 minus x is 46, then x equals 100 minus 46. That's 54. So that's where the 54 came from. Just kind of surmising. That's not algebra, really. Don't go saying it is. Not yet. and we're not going to do it. That's just like I don't know something, so how can I find out? So that turns out to be 54 right there. So that's where I started. I didn't even have this one done yet. So how do I get, this is probably, let's do this one and just I have my reasons. Number 4 is 24% passing. That's what I'm saying. And I wasn't given this. I know this. I surmised this because I took 100 minus 76 and I got 24. So I feel like it's going to be 24 in the cumulative percent mass. But I got to take it all the way back to the mass, not percent mass. So that got me to 24. Now, let's go. Uh, we can do this all the way down, and it gets us to 46%. You know, if it's 46, we were given these, so on and so forth. But we have to, let's just keep going. Let's go from here to, this is the cumulative mass retained right here. Let's see if we can find the mass, the percent mass retained. So real in light, I've got, let's take this 24, because it's the percent, let's multiply it. Let's multiply it times 2,000. And when you multiply a percent, you got to change it. So I'm changing it to 0.24. I'm going to multiply it times 2,000 because that's what we started with. But I'm putting it in a fraction form. So let me clear my calculator. 2,000 times 0.24 equals 480. So I believe that if I take 480, and I did, you can barely see it, and I stuck it here, and if I take 480 divided by 2,000, put it over here. Let me try that. 480 divided by 2,000 equals, no, that's the minus. 480 divided by 2,000, that equals 0.24 times 100 equals 24. So I believe I'm right. Well, let's go back again one more time. Where did that 480 come from? I took the 24 per cumulative percent mass. I changed it to a decimal because I can divide it by 100. To get here, I multiplied it by 100 way back here. But if I divide 24 by 100, I get 2.24, and I'm going to multiply that times 2,000 because I divided a while ago by 2,000. So I'm multiplying times 2,000. I get 480. So 480 is not the percent, but the mass retained. So to get the percent, I take 480 divided by 2,000, and I get, let me see what I get. 480 divided by 2,000. I feel like I'm skipping a spot. 4480 divided by 2,000. That equals 0.24 times 100. So that's going to give me my 24. But we need we need to get back to this 600. How can I do that? Where did the 600 come from? Because that's going to be mass retained right there. What is 600 times divided by 2,000? What is, let's say, what is 30 divided by 100 is 0.0. I'm sorry, is 0.3. So let's call that 0.3. I'm going to divide it by 100. I'm going to divide 30 divided by 100, 100 equals, no, that's plus 30 divided by 100 equals, that equals 0.3 times 100 equals 30. Where am I? Right here. That's percent mass retained right there. So take the percent mass retained. How did I get this 600? Let's see. 0.30, let me clear, divided by 100, 0.3 times 2,000 equals 600. So you take that, you multiply it times, you take that 30 like it was, you divide it by 100 and then multiply it by 2,000, and it's going to give you that mass retained. This over here gave us this mass I'm getting ahead of myself, this percent mass. But let's go through this deal here. Let's take 600. I may be crazy here. Let's take 600 and let's divide it like I'm saying we do, like we usually do. We start with knowing these things. Divided by 2,000 equals 0.3 times 100, 30. Brings us right back there. So the 600, the way I got it was go backwards. Divide this by 100, then multiply it 2,000, and that gave me the 600. Divide this by 100, multiply it 2,000, it gave me that. So that's the way you do that. If you have questions, email me, call me. I'll go through this down here. I try to write these out sometimes when I do that. But if we go from accumulated percent mass, that's where we kind of started, to percent mass, our next step. In case of the number 4, in the case of this sieve, divide the, what did I divide? Divide the percent accumulated mass, which was 24, here we're starting, by 100, and then you take that by 100, that gives you 0.24, and then you multiply that 0.24 times 2,000, that's the total sample weight, and you will get 480, like we got here. You do the same here with this 30, and you're going to get 600. And the way to check yourself is just go back. Go back. See, I had 30 here, 30 here. These are 30 apart, so you're going to have some similarities here. You'll run across that. But then you go back to you're at the 480, right here divided by 2,000 times 100 is, in this case, let's see, 480 divided by 200 equals 0.24 times 100, and that gives you that 24 right there. And then you take 100 minus 24 and you get 76. So we start here and we go backwards by doing this. Take a picture of that if it's understandable. And I wrote over, so there must be something here. Aha. Who knows what that is? This is using a grain size distribution curve. Classify, these are directions, I think, even from the test. Using a grain size distribution curve, that's just something I marked out. Classify the results according to the quality of the soil, poor, well graded, etc., etc. So this is we're going to use the calculation of the coefficient of uniformity and the coefficient of curvature to arrive at some parameters for these soils. So the way we do that is take this, let's see, I'm not going to get to see all of it at once, but we can, first of all, I want you to look at the dashed lines. And then there's one here that goes all the way across. Now what we got to do in this formula for coefficient of uniformity, which is, and the coefficient of curvature, is to find values for the diameter of the particle passing 60%, for the diameter of the particle passing 10%, the diameter of the particle passing 30%. And those will be used in a couple of different places. So the way we do that, we're in a formula state now. We got to get values for this guy, how big they are in millimeters. So let's start with the 60 right here. So we go to the, let's get over here. We got a little bit more light. Let's get over here and let's start with the diameter of the particle that has 60% passing, and then that's its value right there. So I won't try not to get ahead of myself. So we go to 60% and we draw this line until we hit this curve, which is a good curve, well-graded curve, because it covers a wide range of different sized particles. That's the first thing. As a lab tech or engineer, you would notice I probably got a good soil, but we need to go ahead and find these coefficients. So to find them, you take the particle that's passing 60%, and we want to find the diameter. So we go to the curve, 90 degrees, we go down here, and it's 2 millimeters, because here's 1 millimeter, and we don't count this dashed line. 1 millimeter right here, 2 millimeters. So that particle that's passing 60 is 2 millimeters. So we got that down. Now, in the uniformity formula, we're dividing this particle by this diameter right here, which is the diameter of the particle passing 10%. I have so much sinus drainage. Sorry, but we move on. the diameter of the particle passing 10%. Let's find it. So let's go to 10% on our grain size distribution curve chart. 10%, let's go all the way over till we hit the curve here, and then we drop down. And so I'm saying we have 0.3 millimeters for the diameter of the particle passing 10%. So we have 0.1 here, we have 0.2 here, and we have 0.3 here. 1, 2, 3. So that's the way these Similog, these are log scales. I can't really explain it to you. It's based on log 10 and Powers scientific notation, like 12 to the 10th square power. It's just shortcuts, and been years for me. I know a little bit about these things, but not very much. I have a minor in chemistry, and that helps a little bit. But this soil stuff is pretty heavy duty stuff. So now we found the particle diameter of the particle passing 10% is 0.3 millimeters. So we put it here. Now we can solve for the coefficient of uniformity by taking 2 and dividing it by 3/10. Take clear 2 divided by 0.3 equals, I got 6.6, I call it 0.7, and that's good enough for the boys that care and the gals. So 0.7 is our coefficient for uniformity. Now, we know some of these already for the curvature. This is the formula. It's diameter of the particle passing 30% squared divided by the diameter of the particle passing 60% times the diameter of the particle passing 10%. So let's get those out of the way. Let's find the diameter of the particle passing 30%. I sure hope I'm keeping this in your view. Somebody call me if I'm not. So again, we want to find the particle passing, I don't guess we get to see everything at once. 30%. Yep, 30%. So let's go down here to our distribution curve, and let's find 30%. Right here, there's 30%. Let's go over to the curve, and let's drop down. 1 millimeter. Can you read that? Yeah. 1.0 millimeters. That's the diameter of the particle passing 30%. 1. And it's squared, and I squared it right here. Now, did we get the particle passing 60? I think we did. It's 2. But here it is again. Here's 60% over to the curve, down to 2. So it's 2, and it's times the D10 particle, which is 0.3 right here. So 1 squared is 1. 2 times 0.3 is 0.6. 1 divided by 6 is, I've got 1.7. I guess fella could call that 2, but the thing about it is it's greater than 1. Let's say that, because that might be significant, greater than 1. Now here are the what do we call them? The passes, the satisfying. No, these are the results, the parameters. So here they are. The that video that guy gives, I think his name is James or Thomas or something like that. I love that video. He takes you from beginning to to here in that video. It's in at Week 8 Tailgate, I think. Favorite video. Learned a lot watching that over and over. So if the coefficient of uniformity equals 1, right on the money, it's greater than 1 here. All the same size. The particles, the grains are all the same size, and that is poorly graded. Everything being the same, like a bucket of marbles would weigh less if that, a 1-inch marbles would weigh less than a bucket of all different size kind of marbles, because you could get more marbles in there to take up the air voids. Okay, now if the coefficient of uniformity is quite a bit greater than 1, the grain size spans a large range. Look at this right quick. Coefficient is greater of uniformity is greater than 1. What was our coefficient of uniformity? Right here, 0.7. It's not. But if it is, you can see it goes from 3/4 inch all the way over to 1/10. It covers all these different sizes. That's a good distribution. So that is poorly graded, same size, spans a large range. That is well graded. That's if it's quite a bit greater than 1, even up to 10 and 12 and things like that. That's a good good sample, well graded sample. So now if the coefficient of curvature is between 1 and 3, you have a smooth curve. Now between 1 and 3, that's between 1 and 3. The coefficient of curvature is between 1 and 3. So it's a smooth curve, well graded. Now what was on my mind? I can't remember. So if we're in the coefficient of curvature, if the coefficient of curvature is greater than 1, or if it's less than 3, we have a poorly graded soil. Now those, I don't think it asks you these what I call satisfying deals. It satisfies this. That's not what it is. That's an AASHTO. If it's satisfied greater than or less than 50 or whatever we were doing a while ago. Forget the word. But these are the parameters. I don't think it asks you whether it's a good, well graded or poorly graded. But it is going to ask you to calculate this. And I think that problem has a picture of this very same curve. The problem is you don't have, it's going to be on your screen. So you just either kind of, when we were filling in these D's, I used a ruler and went across, but if you see 30 is on a line already there, 60 is on a line already there. So when you get here, they kind of follow lines. So you should get pretty accurate. Remember, the diameter of the particle passing 60%, you go here, and then you go down. Diameter of the particle passing 30%, over to the curve, down. Diameter of the particle passing 10%, over to the curve and down. So that takes care of that. And let's see. There's that monster we went over. I think I'm wrapping up here. And, yeah, you should be able to do this. And this may be what's on the test right here. So if you have any troubles, you can't call me now during the final, but if you need a plasticity chart that we had a while ago, I wonder if we still have it. I doubt it. Where did it go? I have a huge desk. But somehow I'm well disorganized. Well disorganized. Anyway, that plasticity chart I can't imagine. Whereabouts? I put it. I showed it to you. I must have at one time had it in my hands, right? Who knows? Misha, this is a very, very simple thing. I don't know if I'm sure there'll be a given somewhere on here for liquid limit. I just made those up. But you can see all you have to do is if your in this case, liquid limit was 60, 30. I thought I made it 35. Liquid limit, I get them mixed up, plastic. Liquid limit is 35. No, plastic index is 35 right there. And plasticity index, plasticity index right here is 35. The liquid limit is 60. Here's 50. Here's 60. So you have a clay soil with high plasticity. So you have for fine soil, it's not too bad, but that's where you are right there. This 50% line right here, the 50 line they call it, pretty much separates the high plasticity soils, see them, from the low plasticity soils over here. That might be a question. This 50 liquid limit of 50 line goes straight up through here. I think that might be a question, but it's on this side is your low plasticity, and on this side is your, as you can see by the H, is your high plasticity. Good luck. Uh, I think you'll do well. Just remember the usual thing, the shrink and swell on there, and there's so many things that could have been covered, but we covered most of them during the course, and I feel like you'll do okay on this. And, some of you guys have done really well. Look forward to having you again in class, uh, and have enjoyed having some of you been here with me for a while now, and I understand that we're coming close up to where we're going to have September we have a graduation of a couple of guys. I think they'll be our first graduates for the since we started. Excited about that. Have a good rest of the week and weekend. Uh, talk to you later.